I'll introduce our keynote speaker. I know him pretty well now, so. Brian Spears from Lawrence Livermore National Lab is the technical director for Genesis. And this is our new department-wide artificial intelligence initiative. And I just want to say, I'll toot his own horn. Brian works incredibly hard, and he is the vision behind the Genesis program. And so I'm going to turn it over to him and give him a warm welcome.
Okay, good morning. It is a pleasure to be here. Thank you, Dave, for the kind words. I appreciate it. You're going to think that Dave and I coordinated on what we had to say. It's because he's got really strong leadership from NA11, and we are on mission. So when you hear things echoed here, it's because it's actually real. It is really a pleasure to talk to this program today, especially to the current and the recent graduate fellows. I went through a defense fellowship program, and it changed my life, literally. Set the trajectory for my career. It's the reason that today I do science in the national interest. So today, I want to talk to you about Genesis mission with two sub-pieces. One, the nation-scale AI effort that Dave already mentioned. I'll go into some of the details and talk about the promise, the opportunity, the threats, the things that we need to work on. I also thought I would do something novel and actually talk about what I said I would in my abstract. So I will also address the future of scientific work. And in that phase, although all of it, I really want to speak directly to the fellows and the former fellows. So I've reached a point in my career where all of you seem very young and early in your careers. So I want to say some things to you that I wish someone had said to me earlier, maybe even 2 years ago. But any time would have been great before the current moment. So let me jump in and say, I didn't say idea to creation, but I think idea to impact is what we're going to talk about today. It's going from what we think to what we actually have to get done in the smallest time possible, and doing it in a way that captures the current events and the moment that we live in. So we are clearly at an inflection point for science in the national interest, and that's what we're all here thinking about. How do we do that? There are two pieces that I want to talk about. The global security landscape is clearly changing. You already heard that China is emerging as an adversary in the nuclear power race, a newly tripolar world with Russia and with China. There are shifting international alliances that look different than they have in the rule-based order since World War II. And there is an accelerated pace for deterrence that is calling us to take those timescales that Dr. Graf was talking about and shorten them tremendously in ways that are super challenging to our mission. And as if that weren't enough, we live in the midst of a computing revolution. So AI is fundamentally disrupting the way we do technical work. Private industry is now focusing on science at a scale that we thought was all our own, and now that's happening outside our walls. And the funding outstrips the scale of nation states. The GDP of most nations on the planet would be challenged by the kinds of dollar figures that are going into, especially AI, in the current world. You all are building careers and skills at the intersection of those two things for the first and only time in human history. No one else will get a chance to build their personal toolbox and an understanding of their skills against these boundary conditions. So this is an opportunity, and it's also a huge responsibility because you're going to have to generate the ideas that tell us how to do work in the future. So this is, though, what we see already for those of us who are working in the space. AI is disrupting science for discovery and national security. It's a couple of key pieces. There's the strong reasoning capability that we can get from AI, but that doesn't do much for our mission without recruiting the powerful scientific assets to be steered by them. And it looks a little something like the phases that we have drawn across there. We know that AI can help us discover new materials. It's a huge challenge and a giant opportunity. We know that if we discover new materials, we do not just drop them into our existing systems. We redesign those systems to take advantage of the new capabilities and qualities that we've produced. And we've learned it's not good enough to make a perfectly performant system that's infinitely costly to produce. We have to design with the awareness of manufacturing. And we have AI agents that are learning to be sentinels in both those processes and make sure that we don't hamstring the production agencies that Dr. LeGraf talked about when the design agencies are making choices upstream and vice versa. And finally, these high consequence systems get deployed in environments that are harsh to say the least, and they shall not turn to goop 3 months after we manufacture them. So the data we capture for the health of those systems can go back into discovering that material A and material B don't do well against each other. I need a material B prime, and then we can wash, rinse, repeat. We have those glimpses of what to do. What we do not have is the integrated system that pulls that all together in one self-reinforcing system. And so the nation needs a new system for translating ideas to impact. And that is what the Genesis mission aims to be, a whole-of-country effort to harness AI for national impact for the United States. So that mission has two major goals that we've stated. And in sensing the time to impact, we would like to do this by 2028, have the system functioning. On the left, a goal is competitive dominance, to double the impact of US R&D, GDP, leading to global competitiveness. Right now, the US puts about 3.5% of its massive GDP into R&D, and that keeps us near the forefront of most technologies, though we are slipping behind in some places. We want to make it feel like we put 7% of our GDP into our research. That would put us head and shoulders above every other country on the planet. On the part that speaks most closely to my heart is the idea that we call innovation overmatch. That's the idea that we need to be able to mint solutions and mitigate threats on fantastically short timescales so that we can outrun our adversaries, new and old, in any dimension with which they wish to compete with us. That's the goal, the big outcome that we want to go get. So if you set that goal, you have to ask the question, what's the work that has to get done? What does tomorrow have to look like that today does not? And to do that, Genesis has laid out a portfolio of science and technology challenges cut into 3 lanes: energy for the applied energy space inside the laboratory, science for the basic discovery, and the biggest one, national security applications. This is meant to be the sort of periodic table of challenges. The executive branch, the White House, has certified 26 of these to be the mileposts that we go out and get. They look like things like scaling the grid to power the American economy. One that's near to my heart, delivery of fusion energy for the grid. After working to get ignition for 20 years, I love E6. In the discovery science lane, it's things like realizing quantum systems and algorithms. It's bringing to bear actual automated laboratory systems with AI driving to close the loops that we need. And then the most important one, I believe, are all those associated with deterrence. Really, that design to manufacturing loop has got to be the fastest, most impressive thing on the planet to deter our adversaries from threatening us, along with the non-pro and counter-pro missions that we carry in a variety of other things. These are the ideas that AI has to deliver. Or restated, AI doesn't matter unless it moves the needle on these things. That's what we're trying to do. But it's not enough to say these are the changes that we have to have. You have to have some mechanism to get there. You have to have an answer to how are you going to go do that really ambitious stuff. And our answer for that is what we call the Genesis platform. And the platform is pretty simple in concept. The goal is to take AI, as it comes out of Silicon Valley and industry, and use that to harness the 8 decades of build-out inside the department since the Manhattan Project. Mainly our high-performance computing, our precision experimental facilities, and our high-consequence production facilities, and put those in closed, self-reinforcing loops so that we can do the very quick delivery that we've talked about before. That is something that is absolutely the domain of the NNSA. Only we understand how to run the right-hand side of the box, the HPC, the experiment, and the manufacturing. But maybe for the first time really in our history, we absolutely cannot do it alone. The tools that are coming into the NNSA from outside are being built by the OpenAIs and the Anthropics of the world, the AWSs and their services. We're pulling those folks in and making sure that that system we build has the best of the public side, the best of the private side, and is delivering for the entire AI ecosystem for the United States. So the platform is the how we're going to go attack those challenges. So in the idea to impact, we got to have the idea, what do we actually want to go do, and then a mechanism to translate that idea into the actual impact. And that's the basic stratagem that a large team of folks has helped set up inside Genesis. Right now, this year, with the funds that we have from our reconciliation efforts, there are about 1,300 scientists that are running inside the Genesis mission. That's a notion that I'll come back to. you should be thinking about in your careers from the time that you're first-year fellows all the way through working in national interest. What happens when we go to scale? What if it's not just me, but what if it's me and 20,000 of my closest scientist friends working on something? There is a phase transition that can only happen inside NNSA and inside the department. Okay, so to be a little more concrete, without going into too many details, the platform is something like that new operating system for discovery. And I just want to go through a list of what it is and what it feels like so that folks who are touching AI in their research can understand where the frontier is. Can I just ask the fellows or recent graduates, how many folks are pretty routinely touching AI, using it for reasoning or the things that you're working on in science? Okay, that looks like a majority of you. Some of you who are not raising your hand or have not been fellows for a very long time. So what we are using the platform to do is to provide an unprecedented volume of AI. Through Dave's office right now, we have something we call the Model Access Gateway that is pulling Claude tokens, OpenAI tokens into the hands of researchers in unclassified and especially classified environments right now so that folks can start working. But to do that, you do it so that you can harness the HPC, the experiment in production, and have your agent control those things, launch jobs on frontier computers, et cetera. You have to drive workflows that execute at pace. No longer is AI about, hey, I have a really interesting question, help me find an answer. It is, go do this thing in a closed loop, working until you get an answer that I'm satisfied with and come back and tell me about it. The platform's meant to make you able to do that. The one I am most excited about today is capitalizing on our unique data and our subject matter expertise. There's a real memory store layer available now in AI so that as you work on what you're working on in your PhD or your postdoc or as an early career scientist, those systems can help you capture the processes that you are the world's expert in. We can do that at Kansas City. We can do that at Livermore. And most importantly, they're portable now so that we can switch those and we can make our design agencies experts in production, our production agencies expert in design, and do design for manufacture so that we can actually go faster. And the platform is the capability for doing that. We will also train our own scientific models in ways that the frontier laboratories cannot and will not. Ultimately, the only thing that the platform is a way for you, it will be available to you as early career researchers to translate your vision into impact faster, qualitatively better. There's a thing I can't tell you that the platform is going to do. I don't know what it is, because there are going to be things that are so much faster that they are qualitatively new themselves. There will be questions that you can ask and answer that you would not have even thought of if you didn't have these new ways of working. So it's going to fundamentally shift, has fundamentally shifted the way that we do work. There's nothing better than showing you what it actually means. So here is the platform in action through work that the administrator, Mr. Brandon Williams, highlighted in his all hands to us as NNSA employees just yesterday, in fact. We gave a team a goal: develop a flight test vehicle, something that can actually fly through the atmosphere fairly fast, like approaching sonic speeds, get really hot, and let us know what the environmental conditions look like for systems, electronics, things that we want to fly. Can we make them very hot? Can we keep them from getting hot? What happens when we do these things? They picked up the very earliest pieces of the Genesis platform, went after problems that are lined with those science and technology challenges, and are driving a microcosm of the entire nuclear enterprise from idea to creation, from idea to impact. Here's what it actually looks like. Start with hypothesis. Use an AI agent to recruit a topology optimization tool to build out stages inside that flight body. These little conical pieces on the top right fit inside the long flight body to either reject heat or transfer heat into the avionics and the components that are inside this flight vehicle. It's done with a sequence of AI agents and topology tools, which have those things looking very little like a thing I would have designed as a mechanical engineering graduate student. But they're highly effective. They meet all the mission requirements, and they were generated from an array of thousands of ideas with a down selection done to those that match best. A pace that you could imagine doing as a team of humans, but executed with just a few simulation hours of capability. Once that's done, the AI system, through a model context protocol, was actually connected to a prototype printer and a real scale printer, and we went out and built the actual things. Another quick step in going from idea to execution, so that in the next piece, a human could sit in that loop and offer their interpretation and judgment. So a thing we're not doing inside NNSA. We are not taking black box AI and having them certify the stockpile. Human judgment, control, safety, and security is in the loop. It is not the bottleneck, but it is in there. So we will not let go of that capability and that control. Once there was human judgment and we understood that, yes, this would meet safely and securely the needs that we had, then that went into full production with the platform and AI agents driving full-scale production, real additive manufacturing metal parts, 11 feet tall, 1,500 pounds, a gigantic structurally secure system. That was a new workflow for accelerating idea to impact. In this case, the team went a little far with the impact because they dropped it out of a high altitude balloon at 30,000 feet. It got up to about Mach 0.9, and the chute, designed and manufactured by someone not an NNSA, didn't blow, and so it buried itself 20 feet in the ground. So that was impact, for sure. But the system was well designed and over designed, so there was data and a fantastic experiment. 2 to 3 years squeezed down into 5 to 7 months, a factor of 5 to 8 acceleration. That is what we have to go do. That's the kind of thing that NNSA is compelled to do. That is the vision that you set out for the Science and Technology Challenge. The toolbox and the platform that we put together is the how you go get that done. This is the poster child for what we have absolutely got to go do. And thinking like that is what you have to do in your graduate fellowships. Not stuck in a tiny box, thinking only about your local microcosm. Yes, that, but also from top to bottom, start to finish, how do we change the world and the way that we go do things? Okay, this also happens on the science side. What does it look like? You can go from idea to impact, even at basic science facilities. You can lift the same workflows that we are working on, or similar ones, in the NNSA side, drop them into a world-class light source. And what did that team do? That team built an AI pipeline inside the same platform, operating in less secure environments for basic discovery, and went from a 6-month timescale to real time. So there used to be this issue inside science. Folks from startups and from industry would come to the light sources and say, hey, I've got a microelectronic device. You have the bright enough source that I can peer into it and see what's going on. I need you for my business model. And the science side would say, great. It takes us about 6 months from the time we take the image to tell you what's actually inside there. We could do that 3 or 4 times, and then you'd know what's going on. And the answer is we'll be defunded and bankrupt and gone before we could even get that work done, so thanks and goodbye. That team has used the platform to take that 6-month process and shrink it into literal real time so that you can see the image and the object emerge at the light source as you're doing the imaging. What that's brought about is the ability to do 3D non-destructive assessment of microelectronics only in the United States, only at DOE light sources and across the country. That itself will have national security impacts, even if not running inside the secure piece of our effort. So while we have successes at startup scale, we are far from fully capable. So what can we actually do in the AI-driven Genesis NNSA world right now? We can take AI and we can recruit HPC and we can couple it to an instrument. We can drive the 3D printer. We can push El Capitan. We can couple to the largest simulation codes that we've been talking about. But what we cannot do is fully close the loop from that instrument and pull it back to the AI so that in real time we can see what it is that we generated in that instrument. So that's a step that we have to work for. What we also cannot do is have those loops closed and executing multiple times so that you can get an answer, recognize in computational intelligence that it's not sufficient, hypothesize what you should do to be better, and run that loop over again for 5 times, 10 times, over time scales that are not the milliseconds we're used to computing on, but are days of runtime and capability. So we absolutely have to have critical passes with those long runtimes. This is how you change the nature of work for doing science. It's how you get to impact faster. What we also cannot do is the confusogram at the bottom. That's meant to convey that you don't just want to drive one instrument in a closed loop. What you want to drive is instrument 1 and 2 and 3 and device 1, 2, and 3, an entire facility like DART, an entire facility like NIF, an entire computing capability like everything harnessed in Federation across Los Alamos, and Livermore, and Sandia. Those capabilities come from the platform having the connectivity to all of those key assets, the 8 decades of build-out since the Manhattan Project. And those decades of build-out actually matter today when we couple them to AI and we can do facility-level steering. I mentioned that we have a memory layer now so that these systems can remember and understand what they're working on. They can also pass that around. That is the mechanism by which we will couple together, like Lego bricks, these small science factories that are being born into Kansas City, into Y12, into Los Alamos, into Livermore. They can crosstalk and they can move institutional subject matter expertise amongst those and be one NNSA, one nuclear complex, no process drag, no red tape, no friction. Okay, so the red tape and the friction is going to take some other work outside of AI. AI is not the only solution that we need to transform the way that the world is going to operate. But I think it is a necessary condition for us to go do this. So we know how to do this. In terms of technology risk, this is not a huge one. Huge technology risk looks like things that NNSA has already done. We put a marker down and said, hey, we think if you build a big enough laser, and if you shine it in the right way on a piece of fusion fuel, you can probably get it to ignite and produce more energy out than what you got in. We think we've got a good idea from doing things underground. We're not sure if it's physically possible at micro scale, but we're going to go do it. And we did it. We went and made that happen. That is high technological risk, with the United States having the will to bear that risk so that we're the first country on the planet to go do that for our nuclear stockpile. This, we know how to engineer. We can build it today. If OpenAI and Anthropic stop right now and those models get no better, we can still build out these loops in ways that will transform the way we do design for manufacturing, our weapons quality analysis, our safety basis work. All of those things will get better. Okay. The trade-off is it fundamentally changes the way that we do work. So let me transition to the second piece of what I talked about in my abstract, that nature of scientific work and how has it changed, especially for the folks who are earliest in their careers. There are some things afoot in the world changing how you will operate as a professional that you are almost certainly not being taught in graduate school. So I feel like I had the luxury of learning tools from centuries ago that were pretty valuable to me all the way until the current moment. I think you're in a position where you are learning things in an environment that's changing so quickly, it's very hard for anyone to have a curriculum for you, so you're gonna have to do it yourself. You're gonna have to pay attention and have the ideas to understand what is really important. Here's some background in the way that I see it. The first thing that's changed in the way that we work is the level of abstraction. So in programming, this is a familiar opportunity and a familiar story for us. People used to write machine code, they no longer do that. Compilers do stuff for us. There was compiled code, there's interpreted code. You move up the abstraction stack and do bigger things without having to send all the way to the details below those. The same thing has happened, but for the entire way of working with AI. Now, you don't define tasks, the thing you want the computer to do and the steps you need it to take. You need to define outcomes and approaches. Think back to the science and technology challenges, but writ small. What is it that I need to have happen at the end of 3 months of computational effort? What's the outcome we need to get to? And what's the general arc of an approach that we want to take to get there? That's the level of abstraction and thinking that you've got to be thinking about in your career. You have to know what success looks like, the thing we're trying to get to, not the first step on the path to take, but the milepost that you're trying to reach. And that's something that historically we used to ask of people who were senior in their careers. After a decade of working, you would lead a team, you would be the PI in a project, and you would say, here are the outcomes we have to go for, here's how I'll reverse engineer what it takes to do that, this is how I'll get a team to go do it. Both the threat and the opportunity are present for new folks. The threat is you've got to learn that right now. The opportunity is that you've got a force multiplier in your pocket of being able to go get an entire army of computational teammates to go do whatever it is you can dream up to do. And so then it's on you to know what you should be doing and whether you've successfully done it. And I will say from my own experience that using AI tools it turns on my imposter syndrome pretty hard, because I will get answers back from detailed questions, and as I push really hard, I get right out to the end of my reach of what I think I'm a good enough physicist and scientist to know whether it's true or not, and then I feel really uncomfortable. because I'm not sure whether that's a good answer or not. So it's on me to figure out what is the evaluation that lets me know whether that is a good answer. How do I get back to my confidence base where I know it's good and bootstrap myself to confidence or rejection of the idea that that really fast computational intelligence has delivered me? That, across a team of agents, running for days, delivering missions super fast. That is new work that we've got to figure out how to do. Pace. New tools are coming out on something like a 3-month time scale. We did not have Hermes agent, OpenClaw agents, real agents that were super functional like Claude Code and Codex much more than 6 months ago. New agents and capabilities 3 months ago. Who has been tracking the idea of designing loops, engineering loops for AI? Folks who are working on loop engineering. Anybody tracking it? That's the thing. It's the new buzzword in Silicon Valley. Everyone is paying attention to designing the loop. Interestingly, we've been working on the loop for national security for a couple of years now. That's because of where we sit, and I'll go to that further in a little bit later. But those capabilities are becoming a reality sort of every 3 months. And even for the slow and steady part, the mission, the things that both Dr. LeGraf and I talked about for the national and international stage, they're calling us to move an order of magnitude more quickly than we're comfortable doing. Those 15-year ideas have to get down to 3-year ideas. There have to be fast-spinning loops inside that are months, not years, to go operate that. So you've got to be comfortable with the work that you're working on changing. The idea of where you're going's got to be the thing that you're reaching for. The how you get there is disposable. Like the thing we used to fear, I'll have to refactor the code base and all of that capital will be gone. Throw it out. The code base doesn't matter anymore. Okay, not the million-line nuclear codes, all right? Those we're going to keep. Those we're not going to touch. But for the stuff you're doing on a disposable basis, that stuff that is your baby, kill it. Throw it out. Keep the thing you're trying to accomplish. Do it in the best, fastest way possible. Grieve the thing, get rid of it, and be better the next day. The playing field is now completely different as well. So private industry is doing things that I thought was the domain of only national labs. They are hiring interdisciplinary teams. They are going to put enormous investments in things. I thought the space of $3.5 billion lasers was the purview of the United States government alone. There are fusion facilities being built at scales and costs that are bigger than that, outside. There are transformational tools that are coming from outside NNSA for the first time. That is different. So there's a threat there. There is an adversary, a competitor, a peer adversary, outside trying to do the things that we're aiming to do, but faster and better, with less process drag. But that is an enormous opportunity as well, because nothing can motivate you in your career like being afraid to be second. We cannot be second, because we're motivated by what we're doing for the national interest. So we've got to be the fastest, not at developing large language models. That's not our bag, and we couldn't compete. We could compete. If you give us a decade and, I don't know, $100 billion, we'll catch up with OpenAI. So we don't need to do that. We do have to be the fastest at translating emerging methods to impact. And you, as I've said before, have a once-in-a-few-careers opportunity to do this. I used to envy folks who were doing high-performance computing over the arc of high-performance computing as they watched real solid-state technologies be built, the attack of the supermicrocomputer harnessed into high-performance, multi-parallel, massive exascale computers, because they got to build an idea, and as they came in, they put them on their stack, and they just accumulated all of this capability. Like, we all live now in a time that that's happening right now. So the only struggle now is at that 3-month time scale to catch those ideas and put them on your stack and keep them and build that up in real time. It's the only moment in history that we're going to be able to do that without having to go back and figure out why this thing looks the way that it does. Okay, so if there's a little bit of threat from the outside world, why is it that this is the absolute best place to work on the planet, inside science for national security? And it's because we are the only organization that can do what the country needs. Literally, the only one. So you got to think about this. If we're going to maintain relevance in this new age of gigantic companies doing things outside, a level of funding that looks completely different than anything since World War II, go read about the Endless Frontier, check out who Vannevar Bush is, understand the way our funding capabilities are changing. recognize that this is what we do to maintain relevance. First, a steely-eyed focus on mission for the country. You've got to ask yourself the question, what must be done? The second is you have to have a deep knowledge of the solution. How are we going to go do it? The third is an understanding of the power of the laboratories, and I'll say plants and sites, of what we do inside NNSA. What happens if you activate 40,000 scientists to go do something? It's completely different than what happens if you sit in your office and do a really cool thing. We've got to be thinking bigger. So there's you at the intersection of mission, what must be done, capability, how are we going to go do it, and scale. What happens if you activate tens of thousands of people to go do it? And there's a thing that emerges at the very center, which is the public conscience. That's the thing that government-minded science does. We're the only ones asking the question, what's the right way to go do that? How do we make sure that we deter nuclear warfare, that we prevent proliferation, that we counter it when people try? How do we do that in a way that we answer all the colored questions, but in the way that we know is the right conscientious way to go do it? That's our job. You have to have a strong opinion about what it means to go do that work. You've got to keep the national interest in your understanding of progress. Okay. So here's the thing that I wish somebody had told me that now I'm gonna say to you guys. It reminds me of when I was a kid, there was a commercial that would come on television as a public service announcement, and Smokey the Bear would say, only you can prevent forest fires. And as a 6-year-old, it caused me a near panic attack. I was like, how in the hell can it be my responsibility for forest fire safety for the entire country? This is absurd. Turns out my wife thought the exact same thing in a parallel life, and that's probably why we're married now. But only you can prevent forest fires. Like, you are a leader right now. Even if you're a first-year graduate student, you're a thought leader. Once folks have tons of management responsibilities, there are critical, important things they're going to be grappling with. How to do performance appraisals, how to hire folks, how to recruit and keep a pipeline of talent going. But you are at a place where you're thinking deeply about the science. How do I get it done? And all it takes is one super awesome idea that you communicate to your leadership to have impact that is far beyond your years or your capabilities. You're in that driver's seat right now. It's your job to think big, like not small. Not how do I fix line 27 of this code? How do I change the world? No one is going to do that for you. Like, I wish someone had told me that. There is no adult in the room that is not you. It doesn't matter if you're 25, 35, 55. You're the adult in the room with the vision, with the capability to go do it. If you keep that inside, it's gone. It's the Gretzky, you miss 100% of the shots you don't take. So no one has all the answers, but you got to be sure that you have some. And I go back to the next idea. You have to have a perspective. And it takes a lot of thinking to have a perspective. So I suggested already, go read Endless Frontier and the report that Vannevar Bush wrote for how we do science in the national interest. Go read Kuhn's on scientific revolutions. Go read the book Loonshots. It's a book that my laboratory director, Kim Boudil, pressed into my hand, which resonates with the way that I think about the world, tells me a few things about how I can do better. I also think she was subtly calling me a loon while she did it, which if you read the book is probably a compliment, I think. But you cannot do it alone. Like, you have absolutely got to have a team to see what happens when things emerge at scale. And a thing that I've told every person that I've had the privilege to work with and mentor over my career is that the ideas are great, but you've got to be able to communicate them more effectively than anybody else in the room. Like, ultimately, you've only gotten it to the 5-yard line in football if you've had a brilliant idea. It's not until you can get somebody else to see it that you've actually scored the touchdown. And in fact, it's not good enough until you get to the creation phase, until you get to the impact phase. You've got to go from idea to execution, and you can only do that if you can communicate it. Because it turns out the communication is like a wireless device for taking an idea from your head and putting it in somebody else's. You've got to be able to go do that, and the best way to do that is to just say it. I don't know how many times in my career now I've stood outside a room with people far more senior than I and said, am I actually going to say this crazy thing out loud? Like, I am, because I believe it, because I think it's in the national interest, and if I don't say it, nobody's going to do it. You've got to go do that. You've got to go grab it. You're going to fail. It's going to hurt. You will have scars and calluses. If you're not, you're doing it wrong. but you've got to go do that. So that probably sounds a little bit weird if you're new and you're a first-year graduate student. You're like, how the hell am I the only one who can prevent forest fires? Like, why is it my job? But here's an exercise that I do pretty routinely that I suggest everybody go do, because it's actually fun once you go do it. What if it all depended on you? What if you were the only one who could prevent forest fires? Then ask yourself these questions, but about mission. What outcome would fundamentally change how things are done? Like, what's gotta be different about the way we go do things? Can you have an answer for that question? Have you done enough of the thought work, technical and non-technical, to have a perspective? What actions would it take to deliver those outcomes? So here you sort of see the Genesis thing emerge, right? Like, what's the big set of challenges we have to go after? If I'm gonna go after them, how am I gonna enable that to go do that? What do we go do? What happens if you engage scale? What does big look like? How big can you actually go? Can we do the whole country? Can we do the whole world? Like, just ask. What happens if someone gets there first? That question is super sobering inside the national security space. It's really scary. So let's reflect on the change of the way that we do work, the AI harnessing 8 decades of build out to accelerate the nuclear weapons enterprise. Let's reflect on the modernization, actual continued build out that Dr. LeGraf talked about from China. And let's imagine them getting there first. Let's imagine that what I said about innovation overmatch, the ability to mint solutions and mitigate threats on fantastically short timescales so you can outrun your adversary in any direction. Let's imagine they get there first. What does that mean? That's what's got to get us out of bed every morning, and we got to understand the implications of the work that we're doing. And then finally, what's the dumbest possible first step you can take that kicks things off? So I say dumbest in order to be a little bit provocative, but I mean the lowest hanging fruit, simplest thing you can do that will change what we're doing. So this was kicked off, the best example is from NA11, from the RDT&E office of the Model Access Gateway that I talked about inside Genesis. We will preview to the administrator at the end of next week that there are frontier quality tokens flowing through a Model Access Gateway into the hands of scientists and engineers working on national security. Absolutely step zero, the most transformational thing we can do. Huge feedback from folks who can now start to see what the frontier looks like because they have a tool that they didn't have before. They can start to see that the, work is changing is actually real, and they'll have access to it where it matters for them. So what's the dumbest possible first step? You don't have to call it dumbest, okay? What's the easiest, the most basic, the most fundamental, the most transformative? I like dumbest because it keeps me humble and makes sure that we actually keep it focused. But you have got to figure out how to translate that idea into impact for the nation. So that's the view on the way that I believe scientific work is being transformed. So we have got to be the first to deliver a new system for translating idea to impact. And there are 2 ways that we're going to do that. First, we're building the Genesis mission to maximize impact for the United States. Second, you're building you to maximize the impact for the US. And without you, there is no Genesis. There's no NNSA, there's no Department of Energy, there are no national laboratories. The people who certify the stockpile are the people. It's not El Capitan, it's not NIF. Like, these are the things that we're building to go do the most central mission. So I'll leave you with that call to action. Go build you and make sure that we're building the new system together for translating idea to impact. Thanks.